Hi, here we are. This is AS Chemistry from AQA. This is paper 1 from 2016. I've already gone through the first half of this paper in an earlier video, and here is the second half. Right, ammonia reacts with the aluminium chloride as shown by the equation. Draw diagrams to illustrate the shapes of the NH3 molecule and the aluminium chloride molecule. Include any lone pairs, etc., etc. Right. Now, what I would do here is, first of all, I would sketch a dot cross diagram, which I'd cross out because that's not what they want. Actually, so here's aluminium chloride, and we have 3 single bonds there to the chlorines. Each chlorine is in group 7, so I need to draw 6 more electrons for each chlorine. I won't draw it for the other 2, but you know what I mean. Aluminium is in group 3. So I've drawn all of aluminium's electrons. So that means it's only got 6 electrons in its outer shell. So it's got 3 bond pairs and no lone pairs. So that means it's going to be trigonal planar. So let's just draw the aluminium chloride molecule. It's going to be like this. It's going to be flat. And the bond angles are all going to be, there's no lone pairs, and the bond angles are all going to be 120 degrees. Now the nitrogen is in contrast to that. Let's draw the nitrogen here. So I'm going to draw the ammonia. Got NH3, 3 single covalent bonds to the nitrogens. Nitrogen, of course, is in group 5. And I've only drawn 3 dots there, so I need to draw a lone pair there for nitrogen. So that means that for the NH3, for ammonia, we've got 3 bond pairs and 1 lone pair. So those pairs of electrons are going to arrange themselves in a sort of basically a tetrahedral shape. So you're going to have, right, so that nitrogen is in the plane of the paper. This one's, sorry, that hydrogen is in the plane of the paper. This hydrogen's coming towards you. That hydrogen's going back into the plane. Now, if it was tetrahedral, you'd have a 4th bond there. Of course, it's not a bond, it's a lone pair. The lone pair. And that forces the bond angle down. It should be 109.5, but it forces it down to about 107.5. And you'd usually describe that shape as being pyramidal. Okay. That's that bit. Now, name the type of bond formed between nitrogen and aluminium in this compound. Now, what's going to happen here is you are going to form a dative bond. So this thing, the ammonia, is going to, if I paste that in, make it a bit smaller. Right, that's going to go in there. And it's going to form a dative bond. That's not worked very well, but anyway, there we go. So you can see that the nitrogen, the lone pair on the nitrogen, has formed a dative bond to the aluminium. So the aluminium has now got a full 8 electrons in its outer shell. Okay, so let's just see what it says. The type of bond formed, it's a dative bond. And how is it formed? Well, both electrons, both shared electrons, come from the nitrogen. In a normal covalent bond, 1 would come from each atom, but they're both coming from 1 atom from the nitrogen there. Now, the final bit, explain how the value of the chlorine aluminium chloride bond angle compares in Al3 changes when you form this compound. Now, we've seen before, to start off with, it was 120 degrees here, wasn't it? Because you had 3 bond pairs around the aluminium. But here, in this case here, now you've now got the aluminium, you've got 4 bond pairs. And of course, it's not going to be trigonal planar anymore, it's going to be tetrahedral. Okay, so that aluminium is going to have, I draw it here. So you're going to have a chlorine there, chlorine going back into the plane of the molecule, but sorry, let's have a chlorine in the same plane as the paper. We've got a chlorine coming out of the paper, and then we've got this bond to the nitrogen going back in to the plane of the paper. It's tetrahedral, so the bond angle has now become 109.5, like you get in methane. So the bond angle has changed from 120, because it was originally trigonal planar around the aluminium atom, to 109.5 because it is now tetrahedral. Okay. Right, about redox and the halogens. A student oxidizes a solution of hydrochloric acid with a few drops of sodium chlorate 1 solution. The reaction mixture effervesced and turned pale green. The gas formed bleached universal indicator paper. Right. Write a half equation for the oxidation of the chloride ions. Okay, so the chloride ions are out in our HCl. All right. Now, you've got a pale green gas in solution, right? And the gas would be pale green, and it will bleach universal indicator paper. That's chlorine gas. You should know that is. So you've got chlorine gas. So we've got a balance by putting a 2 there. No oxygens or hydrogens to worry about, but we do need to balance the charges by putting 2 electrons in there. That's our half equation there. Half equation for the reduction of chlorate 1 ions to chlorine in acidic conditions. Right, you need to know the formula for the chlorate 1 ion, which is ClO minus. It's chlorate 1 because the oxidation of chlorine there is +1. Right, and that's going to go to Cl2. So we need to balance that, the chlorines there, by putting a 2 in there. Balance the oxygen, so we need to put an H2O on the right hand side. Balance, so we need 2 H2O there, sorry. Balance for hydrogens, well, we're going to need 4 hydrogens, so there's 4H plus there. Now we need to balance for charges. We've got 0 on the right hand side of the equation, but we've got +2 on the left, so we need 2 electrons there. Right, now write an overall equation. So we've got to combine these two in this step. Right, they're both 2 electron processes, so we don't need to multiply or anything, we just need to add them together. So we're going to get 2Cl minus plus 2ClO minus plus 4H plus goes to, well, we've got a Cl2 there and a Cl2 there. That's 2Cl2 and 2H2O, and we can divide everything there by 2, so I think you probably get the mark for that, but it's probably best to put Cl minus plus ClO minus plus 2H plus, because there's Cl2 and H2O. Okay, now this is a hard question and a bit unfair, I think. A solution of sodium chlorate 1 was added to a colorless solution of potassium iodide. Suggest what is observed and explain the reaction that leads to that. Right, now chlorate 1, as we've seen here, is an oxidizing agent. Okay, and what you've got iodide ions. Okay, obviously the potassium ions, like, they're not going to do anything, forget about them, but iodide ions can be oxidized. What can they be oxidized to? Well, to iodine. So that's going to go to I2. And we're going to have to put the 2 electrons on that side of the equation. Now, the reason why I think it's unfair is because it doesn't say that the chlorate ions are acidified. Okay, and if you look here, for chlorate ions, right, you would need some H plus for it, so in order to react to oxidize the iodide. So ClO minus plus 2H plus let's double that. Use that half equation we've got up there. 4H plus and 2E minus is going to go to sorry, that's the wrong half equation we've got. The chlorate ion is acting as an oxidizing agent, so it's going to be ClO minus going to Cl minus. So we need an H2O on that side to balance for the oxygen. We need 2H plus, and we need 2 electrons there as well. Combine those two, you get a full equation. So you will the chlorate will oxidize the iodide to this I2. And what does that look like in solution? It is a brown in aqueous solution. So you'd see that these are two clear solutions. Sodium chlorate's clear, potassium iodide is clear, and the solution would go brown. And the reason why is because you're forming iodine. You don't need to write the half equations there, but I just did that to explain what's going on there. Okay, question 9. Right, a student, right, this is about group 2. Right, so student's getting a powder made from barium chloride and magnesium chloride anhydrous, okay? And he dissolved it in water, so you're going to get Ba2 plus ions, Mg2 plus ions, and chloride ions in solution. And then he added an excess of sulfuric acid. Now, you get a precipitate. Well, you should know here that if you add sulfate ions to barium ions, you are going to get a precipitate of barium sulfate. Okay, so the white precipitate is barium sulfate, and they tell you the mass of that was 0.764 grams. Right, identify the white precipitate. Right, we've done that. It's barium sulfate, and calculate the percentage by mass of magnesium chloride in the powder. So what we're going to do first of all is we're going to find out the moles of barium sulfate, and that of course is equal to mass over mR. The mR of barium sulfate, barium is a pretty heavy atom, it's 137, so 137.3, so that weighs, that's 233.4 for that. So the moles of barium sulfate are 0.764 grams over 233.4, which is equal to 3.273 times 10 to the minus 3 moles. So now that tells us in the original mixture then, we had this many moles of barium ions. So therefore we can say that the moles of barium chloride in that mixture is the same as that. It's equal to 3.273 times 10 to the minus 3. Now, of this 1.056 grams, we need to find out how much is barium chloride. So we can work out the mass of barium chloride there quite easily. Mass of barium chloride is equal to moles multiplied by the mR. The moles of barium chloride, 3.273 times 10 to the minus 3, multiplied by the mR of barium chloride. Now, mR of barium chloride, 137.3 for the barium, 2 times 35.5 for the chlorine gives us 208.3. Okay, so work that out, and that gives us 0.682 grams of barium chloride. Okay, now we need to find out the percentage of magnesium chloride. So we can, quite obvious there, we can just subtract to find the mass of magnesium chloride. So the mass of magnesium chloride is equal to the total mass, which is 1.056, minus the mass of the barium chloride, 0.682, which is equal to 0.374 grams. Now, the percentage of magnesium chloride in the powder is equal to the mass of magnesium chloride, 0.374 grams, over the total mass of the powder, which is 1.056 grams times 100, gives us 35.4%. Okay. Right, now we are on to the multiple choice questions. So which element is in the D block of the periodic table? And they've given fairly, well, 4 elements there, 3 of which are pretty obscure, and lead is like you've probably heard of. Right, let's see where they are. Selenium. Right, so this is the P block, isn't it? That's the P block. This is the S block. And here is the D block in green. Okay. Right, which is in the D block? Well, if you look, it's only tantalum, that one there. Selenium is over in the P block. Lead is in the P block, and antimony is in the P block. So tantalum, pretty obscure element, is the answer. Which species contains an element with an oxidation number of +4? So once we always use our sum of the oxidation numbers is equal to the charge on the species. Right, let's do A. So we've got N, 2 oxygens. That's each oxygen is fixed at -2. So that's -4 for the oxygens, and the charge is +1. So that's +3. So it's not that one. Let's do B. So we've got sigma again for the charge of the oxidation numbers. So we've got chlorine, we don't know. Oxygen is always -2, and there's 3 of them, so that's -6 is equal to -1. That's the charge on the species. Chlorine, that's Cl is equal to +5, so it's not that. Last one, C, H2SO3. So hydrogen is always +1, so we've got +2 for the hydrogens. Sulfur we don't know. O3, that's -6. There's no charge on the species. S is equal to +4. So it's that one there is the right answer. And I think the oxidation number of phosphorus there is going to be +5 because the chlorine is more electronegative than the phosphorus, so they're going to be -1 each. Okay, right. 12, bit of a physics question here, really. Right, so 392 moles in a gold bar measuring that. Okay, what's the density? Well, density is equal to, and the units are kilograms per dm cubed, so it's mass in kilograms over the volume in dm cubed. Right, so we need to work out the volume of this gold block. So volume is equal to 10 centimeters by 10 by 40, which is equal to 4,000 centimeters cubed. And that is equal to, we need to convert it into dm cubed because that's the units we're using there in the density equation. That's equal to 4. Now we need to work out, we need mass in kilograms, but we're given moles. Okay, so mass is equal to moles multiplied by the MR, the AR in this case, because it's an atom gold. So the moles we've got are 392. The AR of gold is 197. That is equal to 77,224 grams. But we want it in kilograms. So that is equal to 77.22 kilograms. I'm going to go over here because I'm running out of space. So density is equal to the mass over the volume. The mass in kilograms is 77.22. divided by the volume, which is 4 in dm cubed, it's 4, and that gives us an answer of 19.3 kilograms per dm cubed. So B is the answer. Okay, so I've just pasted in a bit of periodic table with iron in there. Now, which statement is correct? A, well, I'm going to have to check that later, so I'm going to come back to it. But look at B. The ions of both isotopes contain 26 neutrons. That's definitely going to be wrong without even looking at the number of neutrons, because isotopes always contain different numbers of neutrons to each other. So that's wrong. C is definitely wrong because it says the 53 isotope has fewer protons, 56. Well, we also have the same number of protons, so that's wrong. D, after acceleration to the same kinetic energy, this one will move more slowly than the other one. Well, that is correct, that one, because of course kinetic energy is equal to half mv squared. The 56 isotope has got a bigger mass than the 53. We've all got the same kinetic energy, so that means the velocity's got to be smaller for the 56. All right, let's just check A. It says the ions have the electronic configuration 4s2 3d6. Well, if you look here, that's the electronic configuration of the atom. Okay, so that's wrong as well. Right, iron atom is going to be, look, you've got 2 4s electrons, and then you've got 1 2 3 4 5 6 d electrons, 3d6. But when it forms the Fe2 plus ion, it's going to lose those 4s electrons. The electronic structure will just be 3d6. So that one's wrong as well. So D is the answer. The successive ionization energies for element X are shown in figure 3. Right, now, if we have a look at this, you can see you get this big jump after the third ionization energy here. So that means this element has got 3 electrons in its outer shell. Because of the fourth electron, right, you're obviously dipping into a new quantum shell then, okay? So that means it's got to be in group 3. Right, we've got two elements in group 3 here. We've got aluminium and boron. So how can we tell which one it is? Well, boron has only got, it's atomic number 5. So it's only got 5 electrons. So you can't have, 8 successive ionizations of boron. That's impossible. So it must be aluminium. Which of these decreases down group 2? First ionization energy, that's the one. That decreases down every single group because you get more shielding and greater distance from the nucleus. That's true for every group in the periodic table. Atomic radius actually gets bigger because you're getting a new shell every time. The number of protons obviously gets bigger, and they get more reactive with water because it's easier for them to lose electrons because of this shielding and distance thing. Yeah. So anyway, A is the right answer. Right, we've got this rather complicated looking equation and balancing it. Now, if you're in year 12, that's probably very unfamiliar. If you're in year 13, it's probably pretty familiar. But anyway, let's pretend we haven't seen it. In the balanced equation, we need the mole ratio for sulfuric acid to water. So we need to fill in these numbers here. All right. Now, if we look what's going on here is that, right, it's these oxygens are lost from the Cr2O7, all right? They are lost because what you form, that's got to be a Cr3 plus ion. So we're losing 7 oxygens, so that means we've got to have 7 H2Os there. If we've got 7 H2Os there, we are going to need 14 protons, so that means we also need 7 moles of sulfuric acid there. So let's just check that again, sorry. It's because we've got some hydrogens coming from the ethane dioic acid as well. Okay, so right, those 7 oxygens have got to end up in the water, so that's definitely got to be 7H2O. But we need to think, how many H pluses do we need? Well, we've got 14 on this side of the equation, but there we've got 6 from there. So that means we are going to need 14 minus 6, we're going to need 8 from there. So that means we need 4 sulfuric acids. And let's just check that with the sulfates. That's right, actually. But to check with the sulfates, look, we've got 4 sulfates there. We've got 3 sulfates there, and another one there, which makes 4. So that all works out. So we've got 8 sulfuric acids we've got 4 sulfuric acids to 7 waters. C is the answer. Okay, now we need that equation again in the next step. The next question. What is the reducing agent in this reaction? Okay, so we need to look at the oxidation numbers of the species, right? Okay, so hydrogen and oxygen we can forget about because they're always +1 and oxygen is -2 in all of its compounds. We can forget about the potassium because that's always K+ ion, that's always +1. So the sulfurs as well, we can forget about them because they stay in the sulfate. They stay in the sulfate ion all the time, so forget about them. They're always +6 actually. But so the 2 atoms we need to worry about are the chromium and the carbon. Right, now if we work out the oxidation numbers of chromium in this one, let's do that. So that chromium ion must be Cr2O7 2-, because potassium, of course, is always K+. So the charge on the species is -2. We've got 2 chromiums. We have got 7 oxygens, so that's -14. So 2 chromium is equal to +12. So the oxidation number of chromium there is +6. That's +6. Now let's see what's happened to the chromium over here. The chromium here, well, because you've got 3 sulfate ions, and they have a charge of -2, and you've got 2 chromium ions, the chromium must be +3. So the chromium on that side of the equation has got an oxidation number of +3. So the chromium has become reduced. Right, that means that it's not the reducing agent, it's the oxidizing agent. So the only other element there that we haven't accounted for so far is carbon. So let's see what happens to the carbon. Right, the oxidation number of carbon and carbon dioxide, that's an easy one, that's +4. What's the oxidation number in this ethane dioic acid? Well, there's no charge in the species, 0. We've got 2 hydrogens, that's +2. We've got 2 carbons, and we've got 4 oxygens, so that's -8. So 2 carbons is equal to +8 -2. 2 carbons is equal to +6. The oxidation number of carbon is +3. So the carbon becomes oxidized. It goes from +3 to +4. So the carbon is oxidized. So that means this species is the reducing agent. Now that may seem an awful lot of work for 1 mark, but that's what you've got to do, really. Right, it's that. I suppose you know, by elimination, you could say, yeah, that's not changing. Hydrogen is not changing its oxidation number. Potassium is not changing. It's K+ throughout. And we did show earlier that this one had an oxidation number of +6, and that went down to +3. So that's actually the oxidizing agent. So by a process of elimination, we could have said that that was the reducing agent. That's quite hard. Which substance exists as a macromolecule? So a giant covalent molecule, well, it's obviously not copper. This one we should recognize. Yeah, silicon dioxide is a giant covalent molecule. It's like diamond, don't forget. Yeah, and you've got your tetrahedral silicon, and then each one of those is joined onto another silicon, and so on. You remember that? That's kind of GCSE as well. That one is going to be a small covalent molecule, and magnesium oxide is obviously ionic. So B with the answer there. Okay, so this is quite a hard one as well. So we have a pale brown mixture of these two gases. Right, when you push the plunger in, the mixture becomes paler, so the brown color fades. Okay, now let's see what's happening. So you've increased the pressure. So if we increase the pressure, well, we've got two gas moles on the right and one on the left and one on the right. So if we increase the pressure, the equilibrium is going to move to the right. We're going to get more N2O4, and it tells us that this makes it paler. So that means that this is probably colorless, and the NO2 is the brown one. So we can eliminate. We can say NO2 is brown, so it's got to be A or B. And now it says about endothermic, exothermic. When the syringe is placed in a hot oven, okay, so if we increase the temperature, the mixture becomes darker in color, becomes browner. Now we said the brown color, i.e. the brown color is the NO2, so we've got more NO2. So the equilibrium has moved backwards. So if we increase the temperature and the equilibrium, if you increase the temperature, the equilibrium will always go in the endothermic direction. So backwards is endo. So that means the forward is exo. So our correct answer is A. Okay. 20. Which molecule has the largest dipole? This is quite misleading because you might think, how do you work out which is the largest dipole? Well, there's only one that's got any dipole at all. Okay, now CF4, that is symmetrical. Carbon forms 4 bonding pairs. You've got, tetrahedral. So that CF4, no dipole. Yeah, you have got partial positive charges on the fluorines, but they all kind of pulling against each other. Partial negative charges, sorry. And so there is no dipole, even though the carbon. Okay, so that's not it. SF6 is also symmetrical. If you remember, you've got 6 bonding pairs and no 0 lone pairs. So it's going to be octahedral in shape. For your sort of classic example of an octahedral molecule. So that's not going to be it, even though the fluorines will have a partial negative charge on them. BF3, boron is in group 3. So you've got 3 bond pairs and no lone pairs. That's also symmetrical. Right, so ClF3. Now you don't need to work out the shape of that. But that's the only one. It's got to be that one. Even though there's only a relatively small difference in electronegativity between chlorine and fluorine, they're both fairly electronegative. That's the one, because that's the only one that's got any dipole at all. If you do draw a dot cross diagram for that one, you'll find out that it does have 3 bond pairs and 2 lone pairs, and it usually forms a T-shaped molecule, so it's not going to be symmetrical. Okay, in a molecule of hydrocarbon, the fraction by mass of carbon is 9/12. What's the empirical formula? Now, we'd normally work this out by working out the percentage carbon, then we work out the moles carbon and so on. it's much quicker with when you do multiple choice is to work backwards. So you use a sort of different technique. Now for this one, what's the percentage, what's the fraction carbon? Well, carbon's 12, hydrogen is 1, so that's going to be 12 over 3, 12 over 13, 12 plus 1, that's not it. This one is going to be 12 over 12 plus 3, 12 over 15, that's not it. This one is going to be 3 times 12 is 36, and the whole thing is got an MR of 44, 36 over 44. That is 9 divided by 11. That's the one. This one here, just to show you, 5 times 12 for carbon is 60. 60 plus 12 is 72. So that's not going to be 9/11ths either. So it's got to be this one. And so important to use a slightly different technique when you are doing multiple choice there. Right, this one is about reacting gas volumes. And here we need to remember that if you have 24 dm cubed of any gas, it will contain the same number of moles as 24 dm cubed of any other gas. Also, if you have 10 centimeters cubed of one gas, you'll have the same number of moles as 10 centimeters cubed of another. Right, so what have we got here? We've got xenon reacting with fluorine to form xenon F2. So it's a 1 mole of that, and 1 mole of that gives you 1 mole of that. So we've got 30 centimeters cubed of xenon and 20 of fluorine. So that means we've got more moles of xenon than fluorine. The xenon is in excess. So all the fluorine is going to react, but only 20 centimeters cubed of the xenon react, because that will be the same number of moles of fluorine. So that means we've got 10 centimeters of cubed of that left over. Now, 1 mole of fluorine forms 1 mole of xenon fluoride, so 20 centimeters cubed is going to form 20 centimeters cubed of that one. So the total volume is 10 plus 20 is 30 that's left over. Okay, 23. Which of the following solutions would react exactly with a solution containing 0.05 moles of uric acid? Well, let's do it in terms of hydrogen ions. H2SO4 is a dibasic acid, so if you had 0.05 moles of it, that will give you 0.1 mole of H+. 1 mole of H+ reacts with 1 mole of OH-. Okay. So here we've got, right, how many moles of OH- have we got? We've got 50 centimeters cubed of 1 mole per decimeter cubed solution. So for that one, moles, of course, is equal to concentration times volume, so moles OH. So we've got 1 times 0.05. Right, so this one's wrong because we need 0.1. We've only got half enough. Let's try B. Well, we've got concentration of 2. 2 concentration times, that's 0.1. So that's equal to 0.2. We've got too much OH-, so it's not that one. Let's try C. Well, concentration of OH-, well, concentration of moles of barium hydroxide is going to be concentration times volume. So that's going to be 2 times 0.1, which is equal to 0.2. But of course, 1 mole of barium hydroxide contains 2 moles of OH-, so that's going to give us 0.4 moles of OH-. That's way too much. We need 0.1. So it must be this one. Let's just check this one. Right, concentration times volume, 1 times 0.05. So that's 0.05 moles of barium hydroxide. But of course, 1 mole of barium hydroxide contains 2 moles of OH- ions. So we've got 0.1 mole of OH- ions. So that is the right answer, because this is the, so quite a lot of work for that one as well. And the last question. Okay. Right. So sodium azide decomposes to form sodium metal and nitrogen gas in the airbag. So we're going to get some nitrogen there. But then the sodium goes on to react again, and you get a little bit more nitrogen. Okay. So it says if 2 moles of sodium azide react, how many moles of N2? Okay. So this equation 1, we'll call it. Equation 1 shows us 2 moles of NaN3, that will give 3 moles of N2. So we've already got 3 moles of N2, but it also gives 2 moles of Na. Now equation 2, this one here, that shows us that 10 moles of Na, that will give 1 mole of N2. But look, we've got 2 moles of Na there, so that tells us then from there, so 2 moles of Na, that gives, well, that's going to give, 10 gives us 1, 2 is going to give us 0.2 moles of N2. So we can say the total moles of N2 is going to be equal to, well, we've got 3 there plus 0.2 there, which is 3 plus 0.2 gives us 3.2 moles. But it doesn't ask us for moles, it asks for the number of molecules. 1 mole contains this many molecules, so total molecules is going to be equal to 3.2 multiplied by the Avogadro constant, which is equal to 1.927 times 10 to the 24. The closest one there is that one. That is the answer there. A lot of work for 1 mark there again. Okay, and that is the end of the paper.